at Duke in the statistical science department there. She works on a number of topics, applications of Bayesian statistics, including neuroscience. But looks like what Katherine is going to tell us today is talk about what would, if Thomas Bayes were alive, what would Thomas Bayes and Zuckerberg talk about if they were going to go to a bar? Thanks, Katherine.
Thank you. Thanks. So the title of my talk is Bayesian Modeling of Social Interactions. And this is joint work with Charles Blundell at, well, he was at the Gatsby Unit, Jeff Beck, Wen Dong, and Sandy Petland, who are at the MIT Media Lab. Yeah, so this is supposed to be...
She's got the other mic on already.
Oh, you do? Can we hear? Can you hear her in the back?
The mics are really... The lapel mics on
The board mic on the camera.
Yeah.
Yes. Yeah.
So if I point it more in my direction, can you guys hear me better? Okay, cool. Okay, so people spend a great deal of their lives socializing or interacting with other people. And since social interactions make up so much of our lives, understanding them is a fundamental part of understanding human behavior. And so what we'd like to do is we'd like to be able to make better predictions about people's social behavior and possibly improve the interactions that they're making in order to make them somehow more beneficial. Social interactions are very complex, so analyzing and modeling them isn't really an easy task. And this is really a good area for interdisciplinary research going forward because it can benefit both from the modeling know-how of statisticians and computer scientists and also from a deeper understanding of the subtleties of human behavior that's studied by cognitive and social scientists. Okay, so basically in this talk, I'm going to talk about two projects that I've worked on recently. Both of them have to do with sort of like analyzing social networks and social interactions. The first project is basically, it's called Modeling Reciprocating Relationships with Hots Processes, and it's basically about looking at people's actual interactions within a social network and trying to extract from that some kind of network structure. And the second one is graph-coupled hidden Markov models for modeling the spread of infection. And so that's looking at people's actual physical interactions within a social network over time and trying to determine whether we can predict like who's going to get sick from interacting with whom. Okay. So people are constantly organizing themselves into social groups, for better or worse. These groups might be related to something like an activity, right? Like you belong to a sports team, or something like a role, say like a manager in a company, or just some kind of general social alliance, like members of the same gang. And so understanding the dynamics of these social groups is difficult, but we'd really like to be able to do it. And so one problem that we have is that these groups are often not explicitly defined. So we often don't know who belongs to what group. And we'd like to be able to infer the group structure and make predictions about individual interactions based on this group structure. And there are ways that people kind of go about trying to do this now. And so a common thing that people often do is that they try to leverage declared relationships in order to infer group structure. So by declared relationships, I mean something like Facebook friends, right, where you say, I have a relationship with Joe, explicitly. However, this isn't always really a good idea for many reasons, right? So these kinds of declared relationships, like Facebook friends, are not always available, right? We might not have access to like the Facebook network, or we might be interested in somebody who's not on the Facebook network. They're not necessarily always truthful. Like, I don't know how many of your Facebook friends are actually really your friends, right? or useful for the problem that we're actually trying to solve. And so our goal is to try to infer group structure from actual real interactions that happen over time, which people make with each other. So in what we're looking at, in the data that we're looking at, our data is a sequence of many events, right? They're actions from a sender to a receiver. So for example, I send you an email, and we're trying to leverage patterns of reciprocity in order to discover social groups. And so what this means is that if I respond to your email in the same way as somebody else, we have something in common, and so we belong in the same social group. So this is the kind of data that we're looking at. Okay, so the setup basically here is we have 3 people, Bob, Alice, and Mallory. And say Bob and Alice they belong to the same they all work for the same company. Bob and Alice are some kind of big shop managers, and Mallory is some poor underling that kind of has to put up with them, right? And so we're going to say that Bob and Alice belong in the same cluster, right, because they share the same role in the company, and then Mallory is in a cluster of her own. And so what our data looks like is what's on the bottom right. So I'm going to walk away from the mic, so tell me if you can't hear me. But so these little ticks are basically the data that we have coming in. So the x-axis is time, and the y-axis looks at rates of, say, emails being sent between people in different groups, right? These tick marks are actual emails being sent. The color of the tick marks represents who sent them. Basically the story that's going on here, right, is that Alice and Bob send each other many emails, and they respond very quickly to each other when they send each other emails. But say when Mallory sends Alice or Bob an email, like Alice and Bob take a really long time to get back to her, right? And when they do get back to her, they don't email her as much as she emails them. And so what we're really looking to infer from this kind of data is this clustering structure, which is represented here. The arrows basically represent the expected rates of emails being sent between the clusters. Here basically are the rates of emails over time, right? So we want to infer these rates and this clustering structure. Okay, so in order to build a model that can do this, we start by looking at the infinite relational model, right? So the infinite relational model is a method for clustering entities based on graphs of declared relationships. So now we have to think back to the situation where we actually do have these declared relationships, which are like, okay, I'm Facebook friends with you, and we've declared that, and that's just some kind of binary variable, right? So the matrix all the way on the left is the kind of data matrix that we're looking at. So 1 through 9, say, represents people on Facebook, and so we put person 1 through 9 on the x-axis, and we put person 1 through 9 on the y-axis, and then where there's a black square, that means that those people share some kind of relationship that they've said that they had, right? It's just a binary matrix. Okay, and so what we'd like to be able to infer from these from this data is some kind of grouping structure or clustering structure. So that's right next to the B, right? So person 1, 6, and 4 in the same cluster here. Person 8, 2, 3, 5 are in the same cluster here, etc. And the way that this is done in this model is it said that 2 people belong to the same group if they share the same kind of probability of having a relationship with people in other groups as each other, right? So person 1, okay, so lambda basically represents the probability of intercluster relationships, right? So person 1 basically has a high probability of having a relationship with the people in cluster 2, but a low probability of having a relationship with people in any other cluster. And that's the same for person 6 and person 4, right? That probability of having a relationship with members of other clusters is shared by all of the members of the group. And so what we want to infer, similar to the problem that I just described, is the cluster structure, and then the probabilities lambda of actually having a relationship, having a declared relationship with somebody in another cluster. Okay, and so the generative model that's used here is this variable pi, which is drawn from a Chinese restaurant process. That's what's responsible for assigning people to groups or clusters. The variable lambda pq, which is basically determines the probability of clusters having people in clusters having relationships with each other, right? So it's that matrix lambda. And then basically whether each individual person has a relationship with each other individual person then comes from a Bernoulli distribution based on that probability, right? And so that's how you get the binary data matrix that you see on the left.
So we should think of this as like a stochastic block model with the distribution over the prior distribution over the block structure.
Yeah, so...
and with an infinite set of individuals.
Yeah, that's right. So if you take person 1 through 9 and rearrange them in terms of their group membership, you get this kind of blocky structure that you see in the data matrix, on the output matrix on the right.
So sorry, just one other question, or two other questions, just quickly by way of clarification. So one thing is that the structure you're showing here doesn't show anything about like the rates of email between Alice and Mallory, just whether they have a relationship or something.
Yeah, that's right. So I haven't gotten. So we're going to basically the IRM is like our starting out point, and the IRM can only handle declared relationships, right? So it can only handle these binary matrices, and we want to be able to kind of extend that paradigm so that this kind of model can deal with whole time sequences of events, and that's what we're about to do.
And the other clarifying question was: is the CRP give you a good distribution over group sizes for your application?
It seems to work okay for us in practice. I mean, you can try to use something with a more sort of like even prior structure over cluster sizes, which we didn't try to do. But I mean, you give up sort of like learning the number of clusters.
I don't know what the actual group sizes are actually distributed in reality.
No, I mean, I think for a lot of the data that we're working with, there's not really ground truth, right, for the actual clusterings that are being discovered, right? So it's like I can show you pictures of some of the clusterings that we discovered for particular data sets, and you can sort of subjectively look at them like you would kind of look at like a list of words that belong to a topic and be like, okay, well, this makes sense or this doesn't make sense. But the actual quantitative evaluation that we do is predictive. Okay. So like we just discussed, this IRM model has kind of the right flavor of what we're interested in because we're grouping people together by whether or not they share relationships with people in other groups. But the problem is that this is going off of a binary data matrix where we have declared relationships, and as I kind of motivated at the beginning of this talk, we really want to move away from declared relationships towards actually trying to find this structure based on people's actual social interactions, which happen over some period of time. So we can't model this with a vanilla IRM, and so we can think of ways that we can try to modify the IRM model to get something like that out, right? So we can modify the likelihood of the IRM to use basically a gamma-Poisson observation model instead of a beta-Bernoulli. But then the problem is that we can't predict events into the future. And so instead of using a gamma-Poisson observation model, we consider using a Poisson process. So this would be the IRM generative model with a Poisson process instead of a beta-Bernoulli, right? Our rates come from a gamma distribution, and then our actual events come from some kind of Poisson process. And so you can think of that as taking this binary matrix, and instead of just saying, okay, there's a 1 or a 0, you can think of each of these squares as like a long chain over time where multiple events are happening. Okay, so here our cluster assignments are again drawn from a Chinese restaurant process. Our rates are drawn from a gamma distribution, and then each of our events, which are like emails between pairs of people, come from a Poisson process based on that rate, lambda PQ, where P is one group and Q is another group. But there's still some drawbacks of using this kind of Poisson process. So here the rates of events between pairs of clusters are independent of all other pairs. And the times of events are assumed to be uniformly distributed given a particular rate. And if we think about our problem a little bit, like the email problem, this is not necessarily something we want, right? Because like if you send me an email, I'm probably much more likely to send you an email back sometime in the near future than if you haven't sent me an email in 3 days. So instead of using a vanilla Poisson process, we use a mutually exciting Hawkes process. And so the mutually exciting Hawkes process has the kind of rate structure which is shown at the bottom there. So the idea is that the gamma variable basically gives the underlying rate of me sending you email. And then if you send me email, my rate of sending you an email back jumps up some amount. And then over time, it decays back down to whatever the base is. Right? So this is mutually exciting because it depends on you sending me emails, right? And it's not a homogeneous Poisson process anymore, right? Because the rate is changing. Okay, so the particular function which governs like these jumps in rate is basically exponential. So we have this beta parameter which controls the jump height, and then a tau parameter which controls how fast it decays back down to the baseline level. Okay, so this is the final generative model that we basically end up using, right? So here pi, our group assignments are still come from a Chinese restaurant process. Our rate lambda PQ, so these are groups P and Q, right? So our rate of emails being sent from somebody in group P to somebody in group Q is now governed by this equation, which has the kind of rate structure which I showed you on the previous slide. And then our actual interactions, our emails, say, being sent from somebody in group P to somebody in group Q, is drawn from a Hawkes process based on this rate structure, and then actual individual emails that go from person U to person V is then just determined by a thinning of that particular Hawkes process. And we just use uniform thinning, which basically means that that events are randomly assigned uniformly to individuals within a particular group. Yeah.
So let me see if I understand the thing. This is just, again, clarification. So you're saying that this is modeling group P sending messages to group Q, and the Hawkes process says that will cause members of group Q to send messages back to group P, but not necessarily the same.
Yes,
right.
that's
so
true.
If I send a message to Duke, then that will cause somebody at Duke to send a message back to Johns Hopkins, but not necessarily.
Yeah, so that's not necessarily a good assumption in all cases, and I think that's like totally valid, but it is a good assumption in other cases, like if I shoot somebody in your gang, right, somebody else in your gang might come and shoot me, right?
Sure, right. And, we all talk to each other within our universities.
Yeah. Yeah. So the uniform thinning assumption, thinning can be done in other ways as well. This is just sort of a common way in the way that we happen to adopt. So if you have a Poisson process and you thin that Poisson process, right? So for example, I have some number of events that are drawn from a Poisson process, and then I go through each event, right, and say I have some probability of keeping the event or erasing the event, right? And so say I keep events with probability 1/2 and erase them with probability 1/2. When I erase all of the events after going through each one, and I just look at the events that I have remaining, I can see those events as also being drawn from a Poisson process with half the rate of the Poisson process I drew from originally.
Oh, sorry, the thinning here, you're actually doing thinning. I thought you meant that you were doing allocation of the
It is in fact allocation. You can just see that as thinning, right? Because if you look at any particular pair, it's like a thinned version of what's going on for all of the groups. So all of the events do end up assigned or allocated.
Right, you have this constraint for things sum to 1. Sum up to n pi pi.
Right. I mean, I guess the point here is just that it's a way in which you can see the number of events between each pair of individuals as still coming from a Hawkes process.
Right, but just to understand, if we were to write this precisely, you would be saying that n u1 v1, comma n u2 v2, and so forth would all be sampled jointly from some random allocation process taking n of pi u pi v. Sorry, pi 1, pi 2.
Sure, yeah.
The NUVs for different UV pairs are not sampled independently.
Let me give you a different interpretation. So the lambda PQ simply says message from group P to Q, and then NUV basically says it went from this particular U in V to this in P to this particular V in Q, and so that is a random allocation, and that's done according to the prior pi or whatever it is.
Right.
So in other words, those rates will add up to lambda PQ.
Yes, that's right.
I'm just saying that the notation is only sort of showing the marginals and not the fact that the different NUVs are actually correlated. If n u1 v1 goes up, then n u2 v2 has to go down. Conditioned on n pi, the common p2.
That's correct. Conditioned on that, yeah. Okay, so we can do posterior inference in this model. It's done using MCMC. Basically, unlike the vanilla IRM model, there isn't a conjugate prior for the likelihood, and so we have to sample the parameters instead of integrating them out. And so what we do is we want to infer the partition of the entities, right? We want to infer the group structure, the CRP concentration parameter, the Hawkes process and the Hawkes process parameters. And we do this using a metropolis within Gibbs scheme and slice sampling. And so this is basically Radford-Neal's algorithm 5 with some additional slice sampling thrown in. Okay, and then we ran our model on a bunch of data sets. So here, for example, is a data set from the Santa Barbara conversation corpus. We actually looked at 5 conversations. We looked at the ones with the most people in them. And they represented a variety of social situations, but the one that I'm showing here is city officials discussing a grant application. So in this model, Pat is the chair, and Dan and Rose and Grant are the main discussers, and everybody else is kind of in the audience. And this is the same kind of diagram that I showed you guys before, where like people in the same group are in the same circle, and then the arrows between the different groups basically represent the expected rate of communication going from one group to another. This is another experiment that we did. It's using the militarized interstate disputes data set. And this looks at basically correlates of war. So the data goes from the years 1993 to 2001, basically right after the Persian Gulf War to right before 9/11. And it looks at basically disputes between different countries. And it could be anything ranging from sort of like diplomatic threats of force to actual deployment of force. And so we looked at all dispute incidents in all countries that they track that are involved. And so on the bottom right is a subset of the countries in the data set. So I think there were 82 countries in all. And this is looking at Kuwait, the US, Iraq, Afghanistan, Taiwan, Russia, and China. And so there were three main conflicts that were going on here. So there was a conflict between Russia and Afghanistan, basically coming out of the Soviet war in Afghanistan. There was a conflict between Taiwan and China, basically over potential Taiwanese independence. And then a conflict between the US, Iraq, and Kuwait coming out of the Persian Gulf War. And so this is the particular clustering structure that we discovered. It was kind of interesting to note that more events were initiated by sort of like less powerful countries in all of these disputes. I'm not exactly sure why that is, but I guess maybe the more powerful countries don't have to respond very much in order to make an impact, whereas less powerful countries are kind of, nagging the more powerful countries a lot. Okay, and so this is sort of more quantitative results, right? So here we're looking at the log predictive probabilities of events falling in the last 10% of time for all of these kinds of time series, right? So we run the model on the first 90% of events, and then we try to predict the last 10% of events. And so, what's shown here is log predictive likelihood with standard error also shown. And so we also run this on the Enron data. We look at the 5 longest threads of basically email threads available in the Enron data set. And so we compare the Hawkes process IRM, which is our model, to the Poisson process IRM, which is sort of the intermediate model that I showed you guys. Basically, the difference being that the Hawkes process model captures more structure in rate changes. And then we can also compare to a single Hawkes process and a single Poisson process, neither of which capture group structure. And we compare them on synthetic data, which was the Bob, Alice, Mallory data that I showed you guys in the beginning of the talk, the small militarized interstate dispute data, which was the 7 countries I just showed you 2 slides ago, the full militarized interstate dispute data, which included all 82 countries, the 5 Enron data sets, and the 5 Santa Barbara conversation corpus data sets. And for all of these data sets, the Hawkes process IRM does a better job at prediction than any of the other models. Yeah? It's the predictive probability of events occurring in the last 10% of time. Sorry? As big as you want. Right, because we're dealing with continuous distribution, so.
I mean, I guess if you wanted to get a sense for it, you could have the normalized log probability by the number of events, and then compare that to some kind of entropy of the process or something.
Sure.
That's the way you could get a sense of how much better than random these are, for example. I think that's it. Is that where you're having trouble?
I think the question is this any good?
Right. So these scores are meaningful in comparison with each other, right? And so the intention here is really to compare our model with the other three models that I just described, right? And so what the raw numbers mean themselves, who knows, right? But when you compare them to each other, it gives you some idea of which model is actually making better predictions.
Also, I don't know if you already do it, probably not. You don't divide by the number of events you predicted, right? This is just a total log likelihood.
Yeah, that's right.
So the reason I was asking if you could do a normalized log likelihood is because right now, for example, I don't know whether let's say Enron 1, whether 304.9 is much worse than 335 or not. If it was over 100 events, that's like 3 bits worth of information. But if it was over 1 million events, it's almost nothing. So in some sense, if you had given us a per sample log likelihood, a normalized one, I would interpret it a little bit more, saying, oh, you have a 2-bit advantage over there, and things like that.
Sure.
Okay, but right now, I agree that with Ben that it's hard for me to tell whether this is a worthwhile improvement or not.
Don't worry about me. I'm predicting what someone else is.
All right, so over there. You're to blame.
Right. I mean, really, the point was really just comparison to the other models, right? And it was more like an up or down kind of thing.
I'd like to know how much
But yeah,
information there is in the new model.
understandable. All right. So, so we have a bunch of extensions to this work that we're working on. One's called the Bayesian echo chamber. So the idea here is, I just talked about binary events occurring over time, right? And one could think about trying to incorporate more information associated with these events, right? So if I send you an email, that email has actual content, right? And so that content might be useful in determining something like group structure. So we're looking at integrating dynamic topic models or language models into this framework. And the idea here is that you can also start to pull out other interesting things by doing this, like some sense of power influence, because if you think of power influence being measured by language drift, right? So if you have like a more powerful person and a less powerful person in conversation, right, the language of the less powerful person will tend to drift more towards the more powerful person, right? And this is something that you can actually get a handle on by integrating the language into this model. Sure. I mean, I think that's a good question. I mean, you can potentially try to think up ways in which you could do that kind of comparison. So, for example, if you could get some actual ground truth on the actual clustering assignment or something like that, that's something that you could compare with algorithms which are very heuristic. But, I mean, I think this also gets back to, like, why are we interested in probabilistic modeling or Bayesian modeling in general? And it's because, you know, it allows us to do certain things that are more difficult to do or more difficult to do in a principled manner with just a heuristic algorithm, right? Like predict predict behavior or predict interactions into the future. And like that was one of the things we're really interested in, is like I want to be able to have some ability to predict the interactions we're going to have, you know, going forward, right? And that's something you can get out of a probabilistic model, which is harder to get out of other models.
So this how we evaluate how well we make a case is really interesting point. I'll go back to a little bit of discussion talking about neural systems now. So why couldn't, I mean, you have a model here, and there is data, I mean, real data. Why couldn't create events, okay, generate events with your model, and then use some kind of a, and there is a handful of them, and there is argument which is good or bad, kind of models of how one compares neural spikes. You know? I mean, how does this spike train look like that other spike train? So there is a lot of discussion there how to actually compare this series, which are events like this. Wouldn't that be a...
Yeah, no, sure, you're absolutely right. Like you can use synthetic data, right? And we do in fact use synthetic data, but
generate data, yeah.
So the synthetic data is data that we've generated, and we do look at that and we do compare with that. And in some sense, you're getting a lot of ground truth from that because you've set all the parameters and stuff like that when you've generated the data. However, in a sense, you're kind of cheating, right? Because you're generating from your model, right? So in this case, we're generating from our model, right? And so if our model doesn't do a better job of inferring the structure.
But you also have the data, like the time series data that you were monitoring together. So compare your model now with that, not just because I look at your log data and I say, log unit, that looks good, you know, I mean, what does it mean for the rest of it?
Sure. Yeah. So there might be some other way. Instead of just generating from our model, right, there might be some other way of generating data where, again, we have ground truth. And as long as we think that generation process is an accurate reflection of reality, then that's a valid thing to do and a valid comparison to make. Okay, yeah. So, in fact, the next thing I was going to talk about is an extension to learning clusterings of neurons, right? So similar processes come up in neuroscience to model co-activation of neurons. So basically here we're looking at trying to cluster neurons together by which neurons sort of respond in the same way to spiking data. These models usually also involve inhibition, which is not captured in this model, right? So you'd have to extend it to be able to do that, right? We're only looking at excitation. We'd like to be able to scale up inference. So one way that you can do this is by, for example, saying that, okay, events that happen far enough back in time we're just going to forget about, so we don't have to worry about incorporating them into our model. To deal with unknown recipients, so here we always assumed that we had a sender and we had a receiver, and we knew who they were. But oftentimes you don't actually know who the receiver is, right? And so you'd like to be able to do something like marginalize over all possible receivers, or somehow deal with people who are like broadcasting emails or web pages or whatever. Modeling interactions beyond reciprocity. Reciprocity patterns are one potential thing that you could be interested in terms of discovering group structure, but there are other phenomena that you might want to use to group people together. And then online bullying, it's like, can you use a framework like this to determine things like who's harassing who on Facebook? And it's kind of an interesting question, right? Because you can look at, like, can I actually use rates of interactions like on Facebook in order to, like, discover groups of people who are actually harassing other people? And so that's sort of doing it in almost a de-identified way, right, where you don't actually have to have the content of what they're saying available to you. Okay, so how much time do I have? 15 minutes? Yeah. Okay, so quickly I'll talk about the second thing, which is modeling infection in a social network. So the goal here is to model dynamic interactions between agents in a social network and apply this to inferring the spread of infection, where the spread of infection is actually like a physical infection that's being spread. Okay, so there are many traditional epidemics models which generally tend to work on a population level, treating each person in exactly the same way, right? So you're just one of some population of N people, and there's some rate of spread of some disease within that population, and your chance of having that disease spread to you is exactly the same as anybody else because you're exchangeable with everybody in your population. But contemporary data collection techniques allow us to model the spread of infection on a more individualized level. So I can look at things that are personal to you and then try to make a better decision about whether you're likely to, say, come down with a cold. And so being able to make these kinds of infection predictions on an individual level is very beneficial, right, because it allows people to receive more personalized and relevant health advice. So the data that we used here is from something called the Social Evolution Experiment, which was run by the Media Lab, by Sandy Pentland's group at the Media Lab at MIT. And data was collected, which allows us to track the locations and a contagion in basically an entire community of students over a substantial period of time. And so the idea is that we tracked common cold symptoms in an MIT residence hall from January to April 2009. We monitored over 80% of the residents through their cell phones, taking daily surveys and tracking their location, proximities, and phone calls. Monthly surveys on social health and political issues were taken, and then the locations were taken by having cell phones scanned for nearby Wi-Fi access points and Bluetooth devices. And here's a picture of the student hall network. So all of these students live in the same student hall. Each student is represented by a square, where the number in the square shows basically like their year in school, and then their color shows a particular region of the residence hall that they lived in, and then a link basically is a declared relationship of friendship, which they all did at the beginning. They reported whether or not they're friends with other people in their hall. Okay, so in this experiment, students were paid $1 a day to answer surveys about contracting infection. And the surveys asked about typical sort of infection symptoms like runny nose, nausea, vomiting, stress, depression, fever, etc. 64 of the 85 residents answered the surveys. And the symptoms were, they did significance tests. Basically, symptoms were dependent on the social network structure. Okay, and so what we want to do is we want to leverage this data to predict the spread of infection to individuals in the social network. And we do this using a model related to coupled HMMs. So a coupled HMM is kind of like a regular HMM, except that you have more than one, and the hidden state in a particular HMM at the next time step is dependent not only on the hidden state of that HMM at the previous time step, but is also dependent on the hidden state of the other HMMs in the coupled HMM at the previous time step. Okay, so we use something called graph-coupled HMMs, which is really just a simple extension of a coupled HMM, where we associate with each person in the dynamic interaction network an HMM chain, right? So everybody's got their own HMM chain. Over time, basically the states of that HMM are going to tell us something about whether or not the person is infected. And so the graph structure basically is now going to be based on the social network structure as the social network evolves over time. So if somebody interacts with somebody else, then their state of health is dependent not only on their state of health at the last time step, but also the state of health of the person who they just interacted with. Right? And this is where the spreading of disease is going to come from. Okay, so inference in coupled HMMs in general is very hard. Typically, people do maximum likelihood estimation using very few chains with very few states, or some kind of other approximation is made. And so in the worst case, the graph-coupled HMM inference is basically as difficult as or is exactly as difficult as the coupled HMM inference, right? Because the idea is that if the graph is fully connected, you just recover a very large coupled HMM. But fortunately, since we're actually dealing with social networks, there are a couple of properties that can help us out. So one of them is that social networks are usually sparse. So you can imagine at any given time step, the number of people that any particular person will have physically interacted with is very small. And also for many applications that we're interested in, the influence of interactions can be modeled in a simple way through a very small number of parameters. Okay, so in the case of this data, the influence of other HMMs can be summarized by like counts of interactions in the infectious state. So basically, we're just going to say that like the probability of you becoming infected depends on the number of people who you interacted with who were sick at the time that you interacted with them. So this graph-coupled HMM actually provides an individual level version of the infectious susceptible epidemiology model. So it's a pretty straightforward model, which basically says the number of people who are infected with an illness is some coefficient times a product of the number of people who are susceptible with the number of people who are infected minus some other coefficient times the number of people susceptible. That's basically the recovery rate, right? So it's the infection rate, taking into consideration how many people are available to be infected minus the number of people who actually recover, and basically the opposite for the people who are in susceptible state. You're in either one or the other. So here, the exact graph-coupled HMM that we use is basically just binary, right? You're either sick or you're healthy, you're in a susceptible state, or you're in an infectious state. And everything else falls out pretty easily. So inference in this model is actually pretty straightforward and not time-consuming at all. Okay, so here are the experimental results. This is really just kind of a qualitative result. We had other results in the paper which were more quantitative and comparative. But the idea here is that the x-axis is basically the day, and the y-axis is the student, and the color of the student basically corresponds to the social network that I showed you before. And then the hierarchical structure is basically like basically their interactions or their friendships. And then this is basically a heat map where basically the wider a particular entry is in this matrix, the higher likelihood the model is given to that person being sick at that time. And then the black dots in the matrix basically correspond to how many symptoms the person reported having on that day. Right? So by and large, the hot parts of the heat map correspond pretty well to when people are actually reporting a lot of symptoms, which is maybe not so surprising. But the model is also doing a fairly reasonable job at things like, so for example, one of the things that tends to happen is that somebody gets really sick and then they stop like filling out their survey, right? Because they're sick. And so you end up with these gaps. And so the model is able to kind of like smooth over that pretty well, where you know, it can say, okay, I don't have any symptoms being reported to me, but I still think that you're sick. Okay, so extensions of this model. There are obviously other applications of this kind of model to network data, like modeling the influence of opinions, modeling things that are not physical that are spreading on social networks, scaling up to larger communities, non-parametric Bayesian extensions, and then trying to incorporate, this is a pretty simple model, right? So trying to incorporate other factors that might influence contracting an infection in real life. All right, thanks.
So for the Hawks processes, like if you're doing inference with the CFD, like the standard, picking someone up and then figuring out where you're gonna, like which group you're gonna stick them back into, do you have like a good intuition of sort of like how does the extra expressive power of like this Hawks process and for each individual person sort of like give you, or, like, do you have an intuition for like what table you want to stick them back into, and like why it's better in your final model than the other three? Does that make sense?
No.
So I'm just trying to understand like how the like more complex like probability model sort of changes the way you look at putting a customer back at the table. Does that make sense? We can talk about it offline too. I just didn't know if you had like a quick
And how it affects the movement of the set.
Yeah, so like if I just use like a simple model.
So when you're going to do posterior inference, right, the assumption that's being made in that model is that everybody in a group had the same underlying Hawks process structure, Hawks process parameters associated with them, right? And so basically the probability of their actions being governed by a particular Hawks process, which also has to model other people, is basically taken into account, right? So if my way of responding to people is completely different than yours, then we're not going to have a very high probability of having those actions being generated from the same Hawks process, right?
Yeah. Thanks.
So I'm wondering for the infection model, how it relates to the kinds of things that like an epidemiologist might actually be confronting. So in the situation that you had, you basically knew, well, first of all the people that you were working with were sort of already in very close physical proximity to each other. And then secondly, that you had these declared relationships already. So I guess one obvious question is whether you're thinking about ways of sort of combining that with the first part of the talk where you were trying to infer these kind of relationships, and also, you know, if you were an epidemiologist, is that a sort of a reasonable assumption to have that kind of knowledge ahead of time, or not?
Right. So the declared relationships were actually not really used in the model. I mean, they were used for displaying our results, but they weren't really used in the model. And that we did condition on the graph structure, but the graph structure was actually coming from, at each time point, from their actual interactions, right? So basically, if two people were at a particular Wi-Fi access point at the same time, then there was a link, right? And so that's where the graph structure was actually coming from. But I mean, I definitely think that I think there are a lot of extensions and a lot of things that are not quite realistic about this model, right? It's like kind of a first pass model, and it's sort of like doing, you know, personalized predictive health, right? And I certainly think that there was, you know, there was information that was available because of the confined nature of the population. That might be harder to get exactly right for a broader set of people. I totally agree. You can also think of trying to do other things like using this model to try to predict interactions, like, you know, so people. I mean, one thing we did is we said infections could come from an outside source, which is just sort of like a driving force that was added to the model, right? Because infections can come from outside. But you could think of trying to use this model to actually predict the link structure, the dynamic link structure in the graph. I think that would be a fairly straightforward extension, right? Though you would only be able to do it in sort of like a noisy, missing links kind of situation.
Could you put back the results slide from the first one?
one?
Yeah, thanks. So I think this is a really cool model, and I just want to understand a little bit better where the benefits are coming from. I was comparing the second and third column, and I'm not positive I understand what the third column is. Is that every individual is their own group, or there's just one big group with all individuals?
There's just one big group.
Okay.
Yeah.
I mean, it would be interesting to try both, right?
Yeah,
Both extremes.
so in theory, because we're using a Dirichlet process, because we're using a Chinese restaurant process, putting everybody in their own group is an option for that model. And that's why we don't want to...
But you could do a parametric model where you just have one parameter for every pair of individuals. So especially for something like your international relations thing where there's relatively few actors and presumably enough.
Yeah, that's right. We could do that, and that's actually something asked about a lot, so perhaps we should. But it was, it was a model selection thing done by the Chinese restaurant process, where if that was actually the most likely, most likely CRP, then that would be what would be found in theory.
Right. So the reason that I'm asking the question is, I noticed that in about a third of the cases, if you had to choose between, so the simplest model is the one on the far right.
Yes.
And if you had to choose between enhancing it by cluster structure, column 2, or by self-excitation or mutual excitation, which is column 3. I guess self-excitation must be column 3, because there's only one big group.
Right.
It looks like cluster structure is better in about 2/3 of the cases, but the just self-excitation is better in about 1/3 of the cases. And so this makes me think that there are some times when international relations, for example, just kind of heat up and everybody's sending messages to each other, and that's useful to know. And so this made me wonder whether an even better model might be one that had hierarchical clusters or overlapping groups.
Oh yeah, I'm sure. Right, I'm sure having, particularly as you move to larger data sets, right, having more structure there in terms of the latent structure that you're using in order to model this and to do prediction would be really useful.
I assume that that inference in the Hawks models would be hard if you didn't observe all of the events. So if you had to integrate over events, then it would be hard.
Yeah.
I don't know what the marginal of these processes looks like. So I can kind of see how you would do. The inference slide was quick enough that I'm kind of guessing what you did, but I can kind of imagine if you observe all the events, how you could reassign somebody from one group to another in an MCMC sampler. But it seems like it would be hard to compute the acceptance probabilities if you had to marginalize over events and mutual exciting processes.
Yeah, I haven't worked that out explicitly, so I think that's correct. It seems like that should be correct. But yeah, it wasn't the case that we were dealing with. So yeah.
But you imagine somebody's working with the 1% of Twitter they can get access to instead of the entire fire hose.
Yeah, I think that would be really problematic, right? Having such a low proportion of events available. I'm sure there are ways you could kind of try to deal with that, but I think it would take a lot of effort beyond what's here now.
Thanks.